started to look at that, we wanted to know what the relationships of the microbiomes were to one another. And we already knew the relationships of the host, and yet unrooted philosophy on microbiome. First, it shows you the relationship, in this case, of the bonobos, the chimpanzees, of course, are the most closely related, and of course, the bonobos are fairly closely related. It shows you the different subspecies of chimpanzees, that the humans are most closely related to them, and outside of that are the gorillas. So this is a tree based on mitochondrial DNA. Humans are fairly closely related based on mitochondrial DNA. Our closest relatives are the chimpanzees and the gorillas. So when we look at the community composition, based on the abundance of these OTUs, we got to treat them like this. You can see the terminal branches and the color branches are really long, showing that there's a lot of variation between individuals in the species. But if you actually look at this closely, the interspecies branching order, that's what's coming up in the numbers here, happens to match the tree. So this showed us that host phylogeny actually was a driving force in the divergence of microbiomes. And so you can see the same species here clustered together based on the microbiome. So if you were giving me a sample from any of these species, I could tell you what species it was based on this microbiome. But also, the microbiomes of humans were more closely related to the chimpanzees than the chimpanzee species were most closely related, just like the genetic relatedness. So we looked at that, but of course then started to bother us why the terminal branches so long, and what are the forces that are driving the individual variation within the species. So we looked to a very large data set that was available at the time. The data sets that were available to humans were not as extensive when we first did this analysis, and we turned to looking at chimpanzee microbiomes, because there were lots of samples that were available from chimpanzees collected over the past decades, and the same chimpanzees that take little as we had since 1960. And we took chimpanzees that were from two colonies, the Toma colony and the geographic region, so you can see whether geography played a role in the separation of microbiome. We also, you can see, the genetic relatedness of the individuals, that is, the parents and the offspring, they've all been watched, and so we can tell the samples which individuals they came from. So we had that. We had cases where we had the parents and the offspring. There are cases where the parents and the offspring, and the offspring went into two different colonies. There are cases also, most of the samples came from 2008 10 season, we were trying to correct the knowledge, but also there were samples from 7 individuals who were collected in the year 2000, 2001, 2008, and those are the ones that are cross-hatched collected. So we had in a total of approximately 35 or 40 samples. We did the same exact procedure on that, and we saw what is stored in the microbiome, what is stored in the microbiome. First thing we had to do is find out that zombie chimpanzees do what sort of chimpanzee or zombie has. And you can see here in phylogenetic analysis, the same sort of thing that I showed you before. That all the zombie chimpanzees are more closely related to one another based on their microbiome and on their genetics, and that they were to other species of trans-harmonites, and so they form one sort of cohesive group. To get that, they're all sort of based on the microbiome, so the microbiome community of chimpanzees are all closely related. Here's the phylogenetic analysis, the little coordinate plot showing all the zombie chimpanzees clustered together. Separating out the factors, we saw that there was a geographic structure in the population of the microbiome, so looking at the different microbiomes and finding where they are, you can see the communities can be separated most of the time, or some individuals are intermediate, actually those individuals are reported one community and then move to another one. So it told us that there was a lot of sharing between members of microbiomes and members of the community. There was also some sort of temporal structuring to the data. Those samples were collected in 2008, so this one also sort of clustered together. So there was temporal structuring. Surprisingly, there was almost no genetic structuring to the population. If we look at the overall relatedness of hosts, that is sort of looking at Hamiltonian coefficients related. You're related to your 25 on ham, to your nieces, 75 on water. That's just shown by the blue dots here. The darker blue dots are more closely related. You can see more closely related hosts here don't really have more closely related microbiomes. So this is all the statistics. Because microbiomes are great to be deadly by communities, and it's still by community relation and by gender, but they couldn't differentiate by overall genetic relatedness. Now, while we were doing this work, a lot of information had come out about the human microbiome, and we had many samples. So we were able to have a sort of direct look at the content of the microbiome of humans versus chimpanzees and gorillas, looking at every species. And if you look at the order, look at the taxonomic ranks, not just what the OTUs are, but what the counterpart side, you can see that in the order of 5 of these of all the humans that were available at the time, versus the chimpanzees. You can show here without explaining what the profiles are, that the profiles are about the same. This is the same thing with these three major profiles in the microbiome as the other ones. Looking at the level of bacterial class, they look pretty similar. At the level of order, they look pretty similar. But once you get down to the generic level, that is for the bacterial genus, you can see there's some sharing, and it comes with specific taxa, to no specific taxa, but there are some differences. And at the time, a paper came out that looked at what they call enterocytes in the human microbiome. And this was a pair works. And when they did, looking at 30-some individuals, mainly from Europe and the United States, they found out that they showed that the microbiome is sorted into 3 groups, which they call enterocytes. They were not nation continent specific, they were related to age, sex, or body mass index. And what you have to realize about enterocytes, these are not just 3 groups, but they're based on the relative abundance of different taxa. So we have the enterotype 1 here, which is called the Bacteroides one, that means the prevalence of Bacteroides in the group, and lots of other groups. There's the Prevotella enterotype, that is a portion of high portion of Prevotella, and there's the Pneumococcus one. And so they said that we enterotype based on the overall relative abundance of different genera within the microbiomes. Trying to figure out what the purpose of these enterotypes are, they really existed. There are a few really good papers on it, particularly like this one by Gary Wu, where they looked at the effects of diet, thinking diet, long-term dietary patterns, and you can see some enterotypes. In this paper, some focus on this one. In the audience here, they found 2 enterotypes of Bacteroides and Prevotella, which has different abundance of each one in that. They of course made paper 3 enterotypes and paper 2 in this. It seemed like long-term diet was associated with enterotypes. If you had a high fat, low fiber diet, like most of us had, you had the Bacteroides enterotype, but if you had a low fat, high fiber diet, you had the Prevotella, and they did a nice experiment to see whether they could shift from one to another. So when we started to look at that, we were wondering, are these things real? These specific enterotypes, so we started to think about this. How can we compare this to chimpanzees at the time? Are these human-specific features, or are they beneficial ratings? Now, in a road on this switching diet to a high-fat diet, we should see that non-human primates, they don't really very high-fat diets. But alternatively, if the polymorphism is present and has been contained in other species, then maybe it's a real adaptation. So what did we do? We looked at these zombie chimpanzees in the same sort of study, and we focused on these because they're about the same age as human populations. The zombie chimpanzee population probably rose about 100,000 years ago based on genetic data, and human populations diversified about 100,000 years ago. So we did the same sort of analysis, and we found that the data partitioned into 3 groups, just as we saw in human populations. And in fact, we had the same species driving the enterotypes in chimpanzees and in humans. So you can see here, there's the Bacteroides one here, Bacteroides in the chimpanzee as well. So you have about the same enterotype having the same compositional features in chimpanzees and in humans. Also, as I mentioned, we also had samples that we followed longitudinally. So we looked at this and we found that we had multiple samples for multiple years, and you see in every case that it was a switch from enterotype 2 to 1. There was no consistent pattern among relatives. We have 2 things. So chimpanzees have to be sibling, like slightly different enterotypes, and they had different enterotypes of that. Now, you might recall that I mentioned that you give me a sample of chimpanzees and you give me one from humans. I can always differentiate these samples and tell you whether it's a chimpanzee or a single sample, okay, just based on the content of this microbiome. Okay, so I can separate them. So if you think about this, what does this tell you about the origin of enterotypes? Well, that means they were probably ancestral, that is, before, that is, to chimpanzees and humans. That's why we found some enterotype features in the rivers as well. Which shows that they're ancestral, they were present in a common ancestor, and they've been maintained for millions of years and did not arise as a result of modern life. So if you think about this evolutionary term, you can say there's an ancestral strain here of some genus here, and it's probably the lineage of chimpanzees and humans being separated from millions of years. That's just the genetics of these organisms. And it's very reminiscent of things that are sort of symbionts, that sort of co-diversified with their hosts. So the next thing we did was look at the pattern of co-diversification of microbes, because it gave us the idea that taking microbes somehow co-diversifying with their host. And so we asked the question, did the bacteria co-diversify with their host during gradient evolution? And so this is a cartoon that's taken from a paper by Matthew Moran and Sloan, but it just shows how you can have a community of sorts with different microbes and different hosts. And there's one way where you can have these mistakes, where you can have the obedience cases as well. You can have an environment with lots of microbes in it. You have an environment with many microbes in it, and then the community again is stored as they select from the environment that you get everyone's in it. Or you can have pure co-diversification, that is, you have certain bacteria that are ancestral, and they can co-diversify in the lineages over an evolutionary time. So our prediction, of course, is that because humans and other organisms will take their microbiota each generation anew, and their changes in the individual lifetime that they're taking from the environment, it suggests that this figure here on the left describes that somehow the host select from the environment. So we wanted to talk about co-diversification in gut bacteria, but unfortunately, the type of data that we have makes it extremely difficult to do this. So far, we've been telling you about using competitions, that is, what's the relative composition of one taxon and other relative abundance of these. To find evidence of co-diversification or co-speciation, your first way to do this is to look for the concordance of velocity between bacteria and hosts. And here's a classic example from Matthew Moran data, where you have aphids and endosymbionts there, and you can see the two trees, the one on the left there and the one on the right of the naked host are almost completely concordant, that is, they match, and that gives you fairly good information that these things are co-diversified, in this case, over millions of years. But you can change it from there to take an individual gene, that is ACDA, and follow its velocity to apply the genetic tree of that. But unfortunately, the 16S sequences that we've all been using in order to look at competition evolved way too slowly in order to do this. One OTU may contain sequences diverse from about 10 to 20 million years ago, which is the entire time of the gradient diversification. So we have to start looking at these a little lot faster. So, and this just tells you what I was explaining in the cartoon when I just told you, we have an OTU, but within each OTU, you might have many, many bacterial species or even genera, and each one of those could co-diversify with the host. So we do a slow rate of evolution, 16S OTUs cannot tell you very much about co-diversification, because they have very, very diverse. So we needed to develop a method that had much higher levels of resolution to that. And so to do that, what we did was the same thing that everyone's on the 16S genes, but we do it for protein coding genes. And all you have to read any of it, because it just tells you everything I've already said. All you have to know is what this is that we term this technique called viral tags. So we get 16S tags, sometimes they're called tags, or pyro tags, depending on whether they or L4x4 machine, or we just call these viral tags. So we follow the velocity of an individual gene that's in the microbiome. So we did this, and we focused on a gene called gyrase genes, which is a bacteria, and we focused on individual bacterial families. So if you get some microgorilla samples here, we look at a couple families, Lactobacillus. If you look within a sample of gorillas, in that, we can take all the samples together, we have approximately 100,000 reads. If you look at that, we have a total of 425 of those reads were assigned to Lactobacillus, and overall you get 73 OTUs at 99% level. If we look at the gyrase gene, of course, all of them are targeted to the families, so of course 30,000 reads, all of that, and we get 8,000 tags now, sequences, or OTUs within other species. More impressively, we look at the bacterial ACA, again, we have the same number of reads. There were no reads assigned to this family when getting the 16S genes, but if you target the gyrase gene, you can see we have a 300 of them. So we have much beginning to these OTUs, and sometimes things are not even detected. We have lots of variation. So then we started to do the same sort of study that we did before. Taking the same sample, we have chimpanzees, two pieces of chimpanzees, and gorillas, and humans, which all came from New Haven, Connecticut, from the beginning of time, and we sequenced them, and we have this number of OTUs for each of these cases. So we have the bacteroides, we also tested bacteriosis, and these things are sorted into many species. And what you can see here is that the strain velocity of these different bacterioid species in there matched, in many cases, the velocity of the strain. So this tells us that this were strain or species of bacteroides and cyanobacteria that matched, and that is co-diversified or co-speciation with their grade A hosts. Now people always ask, well, okay, the one at the top here, Bacteroideaceae species 1, what is it? You have a name for this. Okay, here's a species that's co-diversifying with grade A hosts for here. So just for this, we can't give a name, you have Bacteroideaceae proctoriella, or Bacteroideaceae right? Okay, so now if you want to know what species are co-speciating, co-diversifying, that's incorrect. Now this isn't always the case with all the bacteria that we look at. We look into that Lactobacillus, we find many of these, and these things have been transferred many times within all the lineages. So as a result of this, and this is by testing for co-diversification, in humans that have the same microbiome that causes the strain that they're co-diversifying, and those that have been transferred on between lineages for millions of years. If you look at the convergence time, they're co-linear with those of the human host. So this indicates nuclear DNA, mitochondrial DNA, and many of your bacterial genome with diverse fighting construct during evolution. Okay, so now, that is by way of background information. What about microbiomes of the post-current side? So one thing we're looking at is what are the biological tests of this co-diversification? So different human subpopulations have their own strains, much like the factor, using the factor, for example. Different human subpopulations will have their own strains of that. So the co-diversification also occurs within human populations, where there's a transfer of these strains among humans. Also, how far back does it go? To mammals that have these bacterial lineages co-diversify with all mammals. We want to know whether this co-diversification actually denotes co-evolution. Evolutionary biology is basically looking for function in this. Okay, we know these things are co-diversifying, but are they important? Is their functional relevant? If you this chimpanzees have one strain of species, and you have one of the species, is it better for you to have the one that's normal human, or does it matter? It's a chance. These strains are co-diversifying. Also, we developed this phenotype method, but we're now trying to look at metagenomic data, since this is what everyone is producing. We're not going to get these co-diversifying strains from metagenomic data. Instead of taking a completely targeted approach, and we're looking for a lot of data. Another issue that we looked at related to so far, there are absolute abundances of bacteria, or relative abundances. The technique that we've been doing so far in the 60 years, 90 method, and even the biotype, just gives you the relative abundance of the different types. But it could be that some organisms are very awkward, microbiota, and a couple of papers, and hopefully we'll hear about this later. But insects, I'm not saying, even though people have been doing a lot of tagging, not looking at microbiota, they actually have very, very low, there's a paucity of microbes in the microbiota. How do we classify microbes? Not just based on names of microbes, of course, but how do we really classify microbes? The species are at higher taxonomic levels. And also, we've also been looking at now, is one of the unclassifiable bacteria in all these complex communities. So to look at one of these issues, we looked at how much strain code diversification, we looked at metagenomic data sets, and what we did originally is to look at metagenomic data sets that were already available in the case of the Malawian microbiome data sets to see whether we could find any of these code diversifying strains. As we search these data sets for gyre sequences that were part of the right species, and you can see here from bifidobacteria, we find cases where there are Malawians who we found a few sequences of proteins, and in fact, the Malawians are outgroups to other human populations, which is exactly what you expect for genetic data, because that was one of the most ancient human populations. We've done this again, looking at bacteria, we found Malawian sequences and outgroups to sequences that we found in chimpanzees and bonobos, I'm calling this bacteria, not gorillas. Okay, that's not species thing. So we get the code diversifying strain, it's not found in gorillas, it's found in humans, it's Africans, of African origin, and in chimpanzees. So we're finding that of the depths of most metagenomic sequences, we really don't find any of these code diversifying lineages, and we'll search for specific homologs. We'll take this slice a little better when we get a metagenomic sequencing down to somewhere around 100 million reads. We should be able to detect them. Another problem that we've had is how we classify microbes as species of higher taxonomic. Well, you may have seen the paper by Laura Hughes and Bill Banfield, who was published last year in Nature Microbiology, and here they claim that there's a new candidate phylum radiation where there are all these new phylum found in some metagenome certain strains. And they just gave these things, Curtis back here, we heard it, they gave it. So maybe you should go to Stan, John Beck, William Ortiz, they just gave them all their own phylum, different phylum things. Okay, so are these new phyla? Really? How do we tell whether something is a new phylum or a new species? So we want to know how to classify that. And then also, every time I look at a microbiome data set, it has a lot of unclassifiable bacteria. How do we know whether it's a new phylum or not? So one very simple thing that students do in the lab is actually trying to figure out when we have these 60 sequences, are they real or not? So we've been taking small sequences, we've been taking novel primers to that, and just making full-length 60 sequences out, and then trying to classify these later on. And most of the classified ones go already to get assigned to them once we do this. So a lot of things that people call unclassifiable are actually no bacteria, just have these strange variants. A few of them are artifacts, so we can pick up on chimeric checker or other things, but some of them seem to represent new phyla. And I noticed this recently, I saw people with my archive message place group, where other people are trying to look at all these unidentified bacteria that are in the microbiome. These are from blood samples, but they can see by how tiny all humans are found, like many unidentified highly divergent microbes. Okay, so we have all these things that cannot be classified. How do we know what taxonomic right now? How do we classify microbes into a new phylum or species? So for the last few minutes, I just wanted to become an evolutionary biologist video tell you about what constitutes a species. Okay? Now, there's this thing developed by Meyer in 1942, just on the biological species concept, and he defined species as actually or potentially intermediate macropopulations, which are reproductively isolated from other such groups. And this is actually the most common definition of species in used in the Species Act. And the thing about this is it's not arbitrary at all. I don't look at sequence cutoffs, I don't look at a type that's going to say something to species. It's not based on attributes of individuals of a population. That is taking intermediate with one another. And the biological species concept, that is the species itself, is the only taxonomic category that's based on biological process. That is gene exchange, or before you actually have sex. So we can see here, you have interbreeding, reproductive, and gene exchange, gene process. So how do you apply something like this to bacteria or any asexual life for that matter? Bacteria are asexual, they reproduce by binary fission, and therefore they're clonal. They don't reproduce, they reproduce the clones like that. So each cell is reproductively related to other cells. So what constitutes a bacterial species? Maybe it's just a single cell, which just doesn't reproduce. So, in microbiological species concept, how can you classify bacteria and bacteria into species? And the answer is you can't do it. And lots of people have tried. So you'll find paper after paper that's trying to define prokaryotic species or asexual species. And here's a slide from the Herbert Cyclophrony in 2004 at ASM meeting, where he's basically throws up his office on one hand, relationship of prokaryotic species as arbitrary, they're artificial, there's no ending concept, and that is pragmatic. And people define species how they want to do it. Now, we know though that even the bacteria are asexual or gene. Biological species concept. So how do I detect bacterial recombination? Well, this has been done since the 1970s and 80s, work with pioneered by Roger Tiltman. And here's a picture from his penalty for and what he's done. And what he's done is he basically designed some sequences, and he says how much recombination is there. He looks for tracks where there are a lot of changes, whether it's individual changes, and there are a lot of changes that cause against a lot of changes that happen next to each other. He thinks it's a low occurrence, so he says there's a recombinant region of that. And he just counts up the number of individual point mutations versus these blocks. In this case, if you were to count this up, you would find out that there are 10 blocks that are colored as 50 individual point mutations. So he has a estimate for E. coli, he calls the polymorphism introduced by recombination R, and that will be introduced by mutation 10, and he says there are 10 blocks here, 50 here, so R over N equals 0.2. So recombination does affect E. coli in producing variation. So this has been done with many species now that there's a lot of sequencing in place. And here's a quote from Brian Spratt, which he said populations with recombination is either absent or extremely rare, probably represent the minority of situations. There's a backwards way of saying that almost all bacteria recombine at some level. And we show you this, here's a companion table taken by Boston Beetle, it shows you the for all the species that were observed at the time. Here are the clonal species, that is, they have very little recombination, and here are the copper pansic, that means freely recombining population. And you can see the R over N values, whether or not they're zero. Sometimes it's very low levels of recombination, sometimes it's very high levels of recombination. But since there's recombination of all of these, perhaps it's possible to apply the biological species concept. So this is what we try to do, is divide species as groups of exchange genes, just like we do with animals. So how do we do this? We try to detect recombination, and we did this by looking at homoplasies. And so homoplasies, recombination with molecular trees, is where people use these terms. These are characters that are not shared by common ancestry. So to show this on a tree here, with base T, if you combine some sequences, you can see there are very different parts of the tree, have the same base. So basically, this is from here to here, and it looks like a recombination as opposed to being ancestral and lost or all these individual mutations. So we go through all these phylogenetic trees, and we count homoplasies in these trees, and we see things that are pretty a single combination, and you can look at the individual polymorphisms for the entire genome. So our technique was really simple in doing this. Of course, we downloaded all the sequences from species from a GenBank of that. We took away closely related genomes. We defined core set of genes as are genes that are shared by all the taxons in there. We compute genomic distances. We identified the number of homoplastic sites there are versus the mutational sites in that, and we have a definition of how to define homoplasy. And we define this one typical H over N for which is homoplasy versus mutation for every phylogenetic tree. And so this is the only confusing slide that I'll show today, but this is just basically how we calculate this. And so here's a cartoon showing that we have a lot of strains, genome sequences. We were sample 4 strains of it, taking them. Ways that we take a phylogenetic tree, we count out all the ways that we do that 100 times. We do that for 5 strains. We do that all on the N minus subsample strains. And you can see a curve that looks something like this on the acetone. And that thing that we're value is usually less than 1, but there's a lot of homoplasy going on. We take it. Around the 52nd species in there, we're sample just every time. When you sample 4 species, you're going to get a curve that looks identical. But once you start getting that one strain that doesn't recombine, you're going to see the precipitous drop in the distribution. So we look at this continuity, it tells us that we probably more than one species in there. And so we did this with 97. For the 98 strains, over from everyone, this is our result is that the species falls into the category of true biological species, which follows the I've shown you. We have cases that are clonal, that is, we don't recombine at all, the increment is really low, so we can't classify that as a biological species. And then there's cases, like local area here, where the named species, this is GenBank, has sort of discontinuity in it. We just figure out which strains are from a different species. We take them out, we make analysis, and we're happy that way again. If that one species, and we have some strains with another group. By doing this, we're able to classify 85% of all named bacteria into species based on biological species concept. So even though bacteria are asexual, you can apply a biological species concept and apply real species of that. We wanted to see whether the test was robust, so we did it with sex organisms, we did it with fungal malaria, we put some simulate sequences in there. Again, we get the discontinuity, we take out the simulate we get the same thing. We've done the same thing with the chimpanzees in chromosome 21, when we put the sequences of Troglodytes and Homo sapiens, because they find again this nice discontinuity, you can take out the chimpanzee sequence, you get a nice smooth curve of that, which is nice because we know the human studies are bigger chimpanzees and we're separate species. So when we look at that, then we can find out what the limits of diversity there is within a biological species. When people look at 16 sequences, say that 97% identity constitutes a species. However, we see cases where there's a biological species, so that's where the strains in there differ by 30%. So you think that one strict cutoff is not useful at all. That doesn't explain why. Here, there's also Homo sapiens to show you that we're all very closely related to one another. You differ from the person that you find out one base pair out of every few thousand. So now that we can define biological species of bacteria, we're combining this with work that's done by GW group, which is the genome taxonomy database, and what they're doing is they're trying to classify things at every other taxonomic level. So there's new phyla, where you find a rare sequence, which is the phyla, what are the rest of it, just normalizing the distance within a taxon. And now we'll be able to define and classify microbes at every taxonomic level. So we find an unclassified sequence, we can have a genomic sequence of that, we'll be able to figure out what is a new species in the phyla order. So just some general conclusions from what I told you today, and some unresolved issues as we want to think about the future, is host velocity, as significant as the diversification of hominids, is a primary factor of microbiome microbiome disorder or evolutionary concept. We know lots of other factors are going to be introduced in it, diet, ethnography, and so on. But there's a large phylogenetic signal to microbiome. And so we'll just limit our ability to alter microbiomes. There has to be a particular set of microbes that are greater there. Chimpanzees harbor enterocytes that are analogous to those of humans, and host shift among enterocytes over their lifetime. Are enterocytes just stable microbial complexes, or do they affect the host functions? Do they have some function at all? Here are several groups of co-diverse migrating for the next 15 years. I'd like to know, did bacteria co-evolve with human populations I mentioned, and how long, and which strains persist? What types of are co-diversifying, and how they co-evolve with different functions in them? Bacteria reproduce clonally, they differ in the propensity for recombination, therefore we can define true biological species based on virus to gene flow, and so is there a uniform and rational approach to delineate organisms across all domains of life? And finally, don't toss out, ignore, underreport the unclassifiable. See where there's, I tend to think that some of the most interesting bacteria that are sitting in microbiome samples, and people usually don't report them. And I'm asking what are the sources, the origins, and the role of these particular agents. And so finally, I'd just like to give a few acknowledgments to that. The main shout out personally, like Warby, of course I'm very, very grateful to Peter Hahn, who's been collaborating throughout most of these studies, and a couple of terrific postdoctoral graduates, particularly Patrick Jenkins, who worked on chimpanzees, and Andrew Muller, who's now moving to Cornell, has done work on leadership microbiome and co-diversification. And finally, I'd like to thank the generous support for the National Institute of Health. Thank you very much for your attention.
So we have that kind of operations definition of what species is. Kind of just ask you to speculate or amplify on what are the consequences of that for human microbiome negative or positive?
Well, the main thing is knowing whether we're species, whether we combine their genes and we're finding all these taxons, as far as we're concerned, they're co-diverse on co-evolve, we have to know what they are, whether they are the species, as far as genus, whatever. Some of them are functionally important. So we, of course, when we talk about different taxonomic groups, whether they are important now, we can actually, if we wanted to see the human concept and identification purposes, to tell you whether genes have been exchanged between a group or not. Hi, Dr. Good. I think it's really interesting.